Okay, so let's take a look at this first example. Find for values of y which are greater than 0 the general solution of the differential equation dy dx equals xy. So my trigger there is I'm solving a differential equation. The method that I'm learning is to do with separating variables. So what that means is we want to rearrange this differential equation to get all the y terms, so the y dy on one side, and all the x terms, so the x dx's, on the other. And we treat this as if it's a fraction. So we apply our laws of algebra to rearrange this expression. So we've got x times y, so for the y to move to the left hand side we have to do the opposite of multiplying by y, which is dividing by y. So we'll have 1 over y dy, and then the dx will go across the other side. It's a divide, becomes a multiply. So we end up with 1 over y dy equals x dx. And then from the work that you've been doing on integration, you should recognize that if you've got a variable with respect to y, then that means that we're going to be integrating. And that makes sense because as I mentioned in the introduction to this, it's the reverse process of what we were doing with rates of change, where we were going from an expression and developing a rate of change. Here we're going in the opposite direction. We're given a rate of change and we're undoing that differentiation. So that's pretty much the new work. Separating the variables to get the y dy's on one side, the x dx's on the other. Now we integrate. If you integrate 1 over y with respect to y, I'm hoping that you will know that that is natural log of y. And when you're working with logs, you should have the modulus symbol to demonstrate that that has to be a positive value. Because natural log is undefined for negative numbers, we have to put that modulus in. Okay? And then when we integrate x, we get x squared over 2, and we have to put in a plus c. Now we can deal with that modulus easily because it's telling us in the context of the question that y is greater than 0. So y is greater than 0, so we don't need to have that modulus there. So we can just write that as ln y equals x squared upon 2 plus c. Now what we want to have is y equals. So to get the y equals, now we have to undo a natural log. And to undo the natural logs, we take the exponential. Yeah, we take e's. So when we take e's, this side becomes y, and this side becomes e to the power of all of that. So x squared upon 2 plus c. And we can do something here that won't feel natural to you, but will hopefully become natural to you. That this looks a bit messy here, but using the laws of indices, when we multiply things together, like so if we have x to the power of 2 times x to the power of 5, that gives us x to the power of 2 plus 5, which is x to the 7. So we can reverse that concept by saying, right, well, if I've got x to the something plus something, I can write it as a product of the two. So in the same way here, I know that it's e to the power of all of that, which I can write as e to the x squared upon 2 multiplied by e to the c, because the bases are the same, so we can combine those by adding their powers. So it's a reverse to the way we'd normally do that. Now why are we doing that? Well, we're doing that because e to the power of c is just another constant. And we tend to call it a, but it doesn't have to be. Okay, so if it was e to the power of 2, that would be a fixed value. If it was e to the power of 10, if c worked out to be 10, it would be another value. So we would end up writing this as e to the a, e to the x squared upon 2. Now that is a general solution because it's still got a constant in it. So it's a general solution because we aren't given any initial conditions which would allow us to evaluate what that constant is. So if they're asking you for a general solution, that's what you'll end up with.